The Javeriana University, throughout its history, has been characterized by providing its entire community with a superior experience for both study and personal, which is why, faced with the need to comply with certain national and international standards, the initiative arose to develop a plan to improve the high-quality educational experience. The project is located in the city of Bogotá, D.C., at the Cerros Orientales, in a hillside zone in the town locally of Chapinero, at street address 40 and Carrera 5, building 18 of the university campus. It's important to mention that the surrounding structures are Edificio Maldonado, Talleres de Arquitectura y Diseño, Edificio Julio Carrizosa, and the soccer field. So, the following question arises. Why are practice spaces important for engineers? Well, as basic knowledge of engineering is acquired, it is necessary to put them into practice, to have an approach to the professional field. And what better than with multidisciplinary spaces, advanced technology, and tools that allow you to make this possible? The project's conception is based on the sustainable construction of multidisciplinary spaces, considering the EDGE certification approaches as well as the BIM methodology. The EDGE certification 1 ensures cost control and awareness. 2 generates lower utility, maintenance, and repair costs. 3 you can access tax benefits. And 4th allows efficient construction and labor in turn. Finally, we introduce ourselves. We're Atria Ingenieros, a civil engineering consulting company, and we will present the proposal for the development of the laboratory building of the Faculty of Engineering. Now that you know how we develop our work, the scope of the project will be discussed. The creation of a total area of 14,640 square meters provides the opportunity to expand the physical plant of the university for all users with a height of 73 meters. Additionally, and to achieve the EDGE certification guidelines and under the architectural configuration, this area will have wide floors and high heights. Other important characteristics correspond to the creation of a green and open roof, which will result in a space for the creativity of the community and will provide a plus in the scope of energy efficiency. What we bet on with the project is that it's not only a national benchmark, but also in Latin America, thanks to the construction of classrooms with special equipment for each of the engineering faculties. The building will have 15 levels and 3 basements that, in addition to expanding the area offered per student, allows for highly complex design that achieve both level of energy and water efficiency, as well as material use that reduces environmental impacts. The company, Atria Ingenieros, is proud to present a project endorsed by the BIM methodology, through which risks arising from organizational failure are mitigated. Now, it is intended to illustrate by means of the diagram the breakdown of the BIM methodology. Initially, the BIM execution plan was carried out, in which the BIM uses were stipulated as well as the development levels and the definition of the information flow in the platform. Atria is committed to collaborative work, so activities are monitored and controlled progressively in order to make the deliveries in the stipulated times without any kind of problems. The monitoring is carried out from planner and project, all under the commitment to develop a project that meets quality standards, collaborative work, and document management, according to the guidelines of ISO 19650 standard. Knowing the characteristics of the project mentioned previously by means of the BIM execution plan, the planning and communication of the project was stipulated at all times, so that members of each area will be able to streamline problems, avoiding unforeseen events due to lack of information. So that we pride ourselves with excellent team communication, for the lack of communication is the root of problems. Finally, in order to achieve the objective set, the different BIM uses were intertwined, such as capture existing conditions, site analysis, author cost estimate, 3D coordination, design authoring, phase planning, and coordinate design models. An interference analysis was performed in order to avoid cost overruns as well as to reduce the project duration time. Through this analysis, different tests were carried out in order to propose a coordinated and organized model, in which modeling errors are avoided, as well as interferences. In this way, the quantities pulled from the models are accurate. Following this order of ideas, approximately 350 million pesos were avoided in the area of structures. Approximately half of these cost overruns were saved in the area of hydrotechnics. Finally, the areas with the least savings were the geotechnical versus geotechnical test and the geotechnical versus structure test, which do not exceed the 20 million pesos. Finally, approximately 520 million pesos were saved, which is 2.5% of the total budget. Labor savings were much less, being 0.7 of the total project duration, showing the excellent beam coordination that has been done.
First, for the initial conditions, we search for secondary information related with the environment of the project. With this information, it was possible to define the geological formations that are placed in the site like Rio Sicha and Bogota. Then, it was possible to complement the soil characteristic with in situ studies and with the samples collected from the in situ test. It was possible to have a better characterization of the soil. Finally, the average profile is formed by 3 layers of colloidal deposit soil, which mostly is conformed by clays, silts, and gravel, that the rest of a claystone. The groundwater level is located approximately at 20 meters of depth. With all this information, it was established that the response spectrum, in accordance with the seismic microsonic decree, was a result of the transition zone between Cerros and Ladera. As a solution for the retaining system consists in a encouraged wall system. This was defined because of the depth that characterizes the basement place on the building is too high to build a rigid structure. The encouraged wall system consists in 5 types of retaining walls with different heights. They were defined in accordance with the stratigraphy that surround the wall and the surrounding structures. The encouraged act as temporarily because it's planned in a long-term period. The structure can be capable to sustain the retaining walls. For the design, we consider a seismic and static analysis, such for the stability analysis, as well as the design of the anchor on the walls. The construction process consists in 7 steps of excavation, where each of them build a system of berms that act as temporary retaining system, and then in some parts of the excavation level, trenches are built. Finally, on the parts that the trenches were placed in retaining walls is cast on place, then the anchors were placed. Consider the general architectonical description of the structures and the use of space for engineering studies. We propose a steel gantry concentric brace system in which we respect the architectonical proposal in terms of floor height and laboratory spaces. In addition, the material selection and design process consider H standard, looking for energy savings in construction process and useful life, and closed cycle of materials. Part of the structural system is shown in the images, where we can identify the use of type bracing called Cruz de San Andres with 5 columns. Also, there is a description of build area for every floor. The vertical elements location consider building construction requirements like architectonical items and also the geotechnical recommendation. This proposal defines the foundation system. The development of the foundation system consists of complying with the states of failure and service limits according to the stresses given for the columns that rest on the ground. Finally, we designed a total of 27 caissons were obtained with a diameter between of 1.2 and 2.5 meters. 3 caissons are supported on floor number 2, and 5 caissons were made in half moon on the retaining wall sides according to the structural design. There are 3 columns that rest directly on it. The construction process consists in excavate 1 meter of a caisson ring and then cast it in place. Unit the excavation arrives 2 meters or 1.5 meters above the end of the caisson. The structural system is constituted of W beams, columns and bracing with HSS. The floor system considers a metal deck of Corpalosa 3-inch, depth concrete of 140 mm for basement. due to the structural needs in this floor. For raised floor, the concrete depth is 130 mm. We use shear connection of 5/8 inches in every valley of metal deck, as the image shows. In the review, it was established that the use of secondary beams was necessary, this to support the system of collaborating slabs that make up the mezzanine and the distribution load of the main system. During construction and design process, they also consider the hydrotechnical system and equipment in every laboratory and common spaces of the building. The design process was based on current regulation NSR and ASIC. In addition, a lateral bracing for stability must be applied by regulation in the main beam that provides seismic resistance in the system. In the analysis of seismic behavior, we obtain a maximum drive of 0.83% that respect the regulation. The load participation mass was of 91%, and a structural period in direction X of 2.5 seconds and in direction Y 1.9 seconds. There were designed 3 types of ladders, depends of the height of floor and construction space. Due to floors 1 to 3 were smaller than floors 4 to 14. The design considered the human security report and engineering requirements in terms of resistance and load considerations, where we have a minimum with 1 meter and less than 6 meters of horizontal distance. The structural designs propose a section for a stringer and landing of HSS. The ladders were architectonical, designed to provide user comfort.
It's imperative to propose sustainable strategies to achieve the EDGE certification of sustainability for new buildings, where energy efficiency, minimum water consumption, and efficient water use are taken into account, as well as the implementation of environmentally sustainable materials. That's why the implementation of solar panels in the pergola of the 14th floor has been proposed, in order to supply the demand of electrical energy of computer equipment with solar energy. Regarding the hydrotechnics part, the main objective is to reduce water consumption in the building by means of recirculation and recycling of the greywater and rainwater systems. All sanitary appliances that have a supply of drinking water, such as sinks, toilet showers, among others, the systems that are fed by the drinking water network, they will go to a treatment plant and then go to a greywater storage tank, where they will also be mixed with the water that is collected from the rainwater systems. The rainwater system is composed of 2 downspouts that also supply the greywater tank. The first downspout is located on the eastern side of the building, where it's combined with the greywater drainage system from the hydrosanitary devices above. The second downspout is in the western part of the building and functions as an emergency drain in case of presenting obstructions in the first one. After performing the receptive treatment to the water that's stored in the greywater tank, it proceeds to supply the hydrosanitary appliances that make up the greywater supply system, such as toilets and urinals. An automatic system which allows the exchange of volume of water between fire storage tank and drinking water towards the storage of grey water is proposed, with the aim of conceiving a sustainable and efficient building with minimum water consumption. This is done this way so that in case it's required to do a cleaning work, the volume that was stored isn't wasted and can be used in a grey water supply system. The material acquisition protocol is based on sustainable and economic criteria. In the first phase, the information and properties of the materials are compiled. In the second phase, the material resources are quantified along with their waste and their disposal on site and transportation. In the third phase, suppliers are contacted with technical datasheets that have the use of eco-labels. In the fourth phase, the materials are acquired looking for payment condition and guarantees of durability of the material. and in the last phase, a space is determined with labeling of quantity and location of each material with inventories.
The construction of engineering building of the Pontifical Javerian University is located within the university facilities. Certain measures established in the Territorial Ordering Plan, POD, of Bogota are not necessary, because the closest neighbors are some of the other buildings of the university campus, thus provide an advantage in the terms of decision-making related to the work. However, different permits are required from the Mobility Secretary to properly organize and control the entry and exit of vehicles to construction site. The main construction stage of the project can be defined in demolition stage. In this stage, the purpose is to reduce environmental impacts and others that may affect the environment. Excavation stage. The moment of the excavation process is sought to be as careful as possible both with nature and with neighboring buildings and public service pipes. Construction stage. During this stage, the aim is to establish an adequate space for the storage of different materials, seeking to maintain safety at work. For all the stages of the project's internal and external SECNEC was implemented for the entrance of the work to guarantee the safety of the work and external personnel.
Regarding the project durations, a total time of 964 days was obtained, which is divided as follows. First, preliminary activities 44 days. Second, foundation system 412 days. Third, structural system 452 days. Fourth, environmental management plan 35 days. And finally, installations and services 58 days. And finally, let's talk about costs. The total price of direct cost is 23 billion pesos colombianos, which is divided into the same chapters and sub-chapters as the durations, which we present below in the slide. It's important to mention that all these prices are in pesos colombianos. The preliminary activities have a cost of 400 million pesos. The foundation has a cost of 5 billion pesos. The structure has a cost of 23 billion pesos colombianos. The environmental management has a cost of 66 million pesos. The facilities and services have a cost of 300 pesos colombianos. And now for the AIU analysis, we have a 14% administration that gives 4 billion approximately, a 9% of contingencies that gives 2 billion pesos colombianos, a 6% profit that gives 1 billion approximately pesos, and finally a 19% tax of profit that gives 300 million pesos colombianos, for a total project cost of 38 billion pesos colombianos.